My name is João Casal. I'm the head of R&D of One Global. One Global is an expert on SIM technology and providing connectivity services all around the world, global connectivity services for IoT or for consumers. And today I'm here to talk about the SIM and cellular network roles in seamless authentication and trust, which is part of the work that we do in ARCADIAN-IoT. So regarding the agenda, I'll start by two intros, in fact. The first one on SIM, the SIM unique positioning for IoT cybersecurity. And the second intro is on very fast intro on programmable networks for building automation in a security sweet spot, which is related obviously with the cellular networks. After that, I will present our solutions for ARCADIAN-IoT, particularly the SIM and programmable networks as security enablers. I'll try to save some time for questions and answers at the end. Moving to the SIM unique positioning for IoT cybersecurity. First of all, starting with the concepts, the SIM stands for Subscriber Identity Module, and it allows a cellular device, any cellular device, to connect to a mobile operator. It has an hardware secure element with computing and storage capability that stores, in one hand, phone numbers, contacts, and text messages, but stores as well cryptographic material and unique identifiers like the authentication keys, the IMSIs, the International Mobile Subscriber Identity, that are needed for the identification of the subscribers in the networks, the mobile country codes, and so forth and so forth. So the SIM is already used nowadays for identity and for authentication, and is used very broadly, right? So one claim that I would like to make is that the SIM is already a security enabler proven by billions of devices, and this is a claim that probably it's easy to do because any cellular device already has a SIM. The number of connected devices, it's on several billions and is growing. And moreover, we expect that in the future networks, new SIM security functions will continue to appear. And I will talk about some that are part of working groups that we are working with. Thinking a bit on the SIM and on its security functions and if it is really secure, a question that I would like us to think on is if the SIM is really secure or if it simply doesn't protect anything relevant for attackers. So to think on this question, I have here some sentences for allowing us to build on this concept. So if one attacker would compromise a SIM, he or she could, for instance, get mobile internet for free because it would get the identifiers and the keys to get the services from the mobile operator. It could get it for free for himself or for selling it in the black market. It could impersonate a person in phone calls and SMSs with all the private data that is around our phone calls and SMSs. It could get bank operation confirmation codes from the subscriber, those ones that we receive when we are doing transactions, bank transactions, for instance. And considering that, for instance, SMSs are being used for sending one-time codes for accessing websites, attacker could access as well the public services that are available on websites nowadays, having access to information like personal incomes, household address, family member names, again, very confidential information. So it's easily well accepted that the SIM is hard to compromise nowadays. It is trusted by network operators, banks, governments, and even by ourselves because we use the mobile devices with quite a lot of confidential data. And GSMA even claims that the SIM can be used as a hardware root of trust for IoT, and I will evolve this thought a bit in the next slides. Just to understand the evolution of the SIM in the last years, so it born in 1991, quite a long ago, And since then, its evolution got this element lower in size with less plastic. But in the last evolution, we believe that it got to be a radical innovation from the nano SIM to the eSIM that grants more automation and more security. More automation because for the ones that didn't try eSIM yet, it allows to the digital download or upload of the SIM profiles to the device. There is no plastic card to put in the device. It's just a matter of downloading a SIM in the case of consumer devices or upload a SIM profile in case of IoT devices. And more security because, again, there is no plastic card to put in and out of the device, and it's soldered to the board, so it's harder for an attacker, for instance, to do SIM cloning because you can't get the SIM out and put in a machine to clone, which is very rare, but it's one of the attacks that exists to the SIM. So it's moving to be even more secure. And another relevant aspect regarding this latest evolution is that it's being pushed by the big manufacturers like Apple and Google. Apple already launched several, at least two, eSIM-only iPhones, the ones on the top of the brand. And there were also rumors regarding Pixel 8 being or having a version that was eSIM only. This was not the case, but in fact, since Google Pixel 4, that eSIM is already present. So Google is also pushing for the eSIM technology. Moving a bit to the standards or to the new specifications that are being built for the SIM, for the new security features of the SIM, GSMA is proposing GSMA IoT Safe, which claims that the SIM can be used or defines specifications for using the SIM as root of trust. The image that you can see defines exactly the components of this specification, where you can see in the bottom left the SIM IoT security applet, software that runs on the SIM that is in the device, in the IoT device. And then GSMA standardizes, let me put just the text here, GSMA standardizes, for instance, that middleware and the interactions between that middleware and the middleware of the device and the middleware of the backend. This middleware of the device allows exactly the client application of the IoT device to interact with the SIM. This is what needs to be very well specified. And in the other side, the middleware of the server and the communication with the server application is exactly to have a secure ship-to-cloud communication of the data. So this specification defines the SIM as a mini crypto-safe inside the device. It allows to establish the secure connections that you can see in the diagram, for instance, DTLS, and keep long-term secrets safe. So secrets may be generated in the SIM, in the hardware itself, and be kept there without any way of accessing it. So we can assume to be safe because the SIM, as far as we know, is very, very secure up to now. This technology is compatible with any SIM form factor, SIM, eSIM, iSIM, any SIM form factor that exists nowadays. It provides that common API for interacting with the SIM that I described to be the IoT device middleware, and helps solving the challenge of provisioning millions of IoT devices. For instance, using that IoT security service that you see in the bottom of the backend, communicating via OTA with the SIM security applet. I will provide some examples of the use of this specification from GSMA in the work that we did in ARCADIAN. Okay, I will provide them in a few slides. Moving a bit for the intro on programmable networks, and in this case, we are focusing on automation in what we consider to be a security sweet spot. I'll start by just presenting a very high level and overall view over cellular networks, where in one hand we have the devices that communicate through radio access networks, and they want to communicate with the internet, with other public or private networks, with other devices, other servers. In the middle, we have the core backbone network that has the call control functions that interconnects different networks, that has the authentication functions that use the SIM exactly for this authentication. We also have the policies and charging functions and several other functions that belong to this intermediate area between the devices and the internet. So what we can understand or can easily accept as well is that here we have a more trustworthy area. I'm not claiming that is completely trustworthy. I'm saying that is more trustworthy than the other one. In this case, it's more trustworthy because it uses a licensed spectrum. It uses the data in the SIM to do the authentication. It uses security standards that are in use by billions of devices. So it's more trustworthy than this area here between the core network and the internet itself, because it's where we know that there are more threats from unknown networks, unknown servers, unknown services, or other devices. Moving a bit with the rationale, I would like to claim that the core network is a cybersecurity sweet spot because it is in the intersection between a more trustworthy area and a not that trustworthy area. So we are able, if we are able to act in that spot, probably we can have very effective cybersecurity actions. So just to showcase this, let's consider how manipulating a basic network function can contribute to cybersecurity. For instance, putting rules here in the policies and charging functions. And the variable that I would like to showcase is exactly the bitrate that we can define there in those functions. So if we manipulate the bitrate uplink or downlink, we can, for instance, avoid private data leakage. So if we reduce the bitrate to 0 in the uplink, the private data leakage stops. So it's a way of stopping this attack. In the other way around, we can stop unauthorized device access or control. So if we reduce the bitrate to 0 in downlink, if the device was being controlled by an authorized entity, we were able to stop it. DDoS botnet, the same rationale. So if we know that a device is part of a DDoS botnet, we could stop it. Impersonation attacks, the same. Data poisoning, the same. So just by manipulating the bitrate, we would be able to act in protection or reduction of an attack impact. I'll give a more concrete example of this exactly in what we did in ARCADIAN, okay? So moving exactly to that, to the solutions that we have in ARCADIAN and that we propose, or that were target of our research in ARCADIAN. I will not talk about the project. Sergio already did that. What I will talk about is what is the role of a SIM. We started by a SIM, but in fact the technologies that we developed are appropriate for any SIM form factor. So they work in a SIM, but also in the regular SIMs and iSIMs. So what's the role of a SIM? Obviously, the cellular connectivity enablement for the use cases that we have. Also, new identity and authentication processes, which I will describe after. And to act as root of trust for security. For instance, for darknet encryption that you can see there, Attestation also uses the SIM as root of trust. And then there are actions that are triggered by the SIM of self-recovery and self-protection. And what is the role of programmable networks here? Mainly, we use programmable networks to act in authorization, particularly to enforce trust-based communication policies. We also use the prognet to distribute the trust information that we have to the devices, particularly to the SIM. As it probably is getting obvious, we need to receive this information of the trustworthiness of the devices and of the entities from somewhere, because we are not able to infer it. So that's why the reputation system is already excelled in that yellow box below the authorization. Then there is the interaction with the SIM for the trust-based information distribution, which will trigger self-recovery or self-protection actions, and also work with hard-net encryption. I will describe this in the next slides. Starting by the first solution. So the first solution that we provide in ARCADIAN is a zero-touch network-based authentication of IoT devices to cloud services. What do we want to tackle with this solution? The problem is that IoT authentication in cloud services is still hard, because there is the credential provisioning that needs to be made, and this being made in manufacturing time is costly and sometimes hard to scale. For instance, there are cases that there is a need to connect a proprietary system to a dedicated hardware to insert the credentials device by device. This is quite hard to scale, and this is a problem that we would like to face with our solution. Also, there are practices that are not well accepted as secure, like the use of hard-coded username and passwords, which is still a practice. So we would like to solve this as well by providing a zero-touch network-based authentication that would be very well received by manufacturers. So the solution that we provide is to leverage the cellular authentication that is standardized and the SIM credentials that are already in the SIM to authenticate the devices, not only to network services, which is what already exists, but authenticate IoT devices to cloud services. And that is the main difference. So the solution, in fact, is not very complicated. You can see it here. I will describe it step by step. The first step is that a device with a SIM there, can be a SIM and a SIM whatever, needs to first authenticate in the core network according to standards. That is the step one that you can see there in the top left. After that, and this is the novelty, the device will request the authentication in a given cloud provider. By doing that request, we have a new component here in the middle. I will put my mouse, I hope that you can see it. This new component that we have built will verify in the network core databases if the subscriber is known and if it has access to that cloud provider. And if so, it will issue a network ID token protected and signed by the network provider. With that network ID token in the cloud service, it is possible to verify if that network ID token matches the device ID that registered with that network ID token. So it's a verification that can be done in several ways. In this case, we just describe it as a signature verification and of the match of the network ID token to the one that was previously registered. This solution, in fact, is quite lightweight, so no new cryptographic material is needed, just the SIM secrets and processes for the authentication according to standards. There is no new hardware, just the SIM, a SIM or a SIM that the device already had for connectivity. We believe that it is secure because it leverages proven security standards, and that it is quite scalable because there is no added effort on IoT device manufacturing other than putting there the SIM. Moving to the second solution that we provide, this is the use of SIM as root of trust for hard-net encryption, and this extends to remote attestation, but I will focus just the use in hard-net encryption. The problem was how to add the root of trust information to harden the encryption process. Why? Because there is an opportunity to, for instance, harden this encryption with the mitigation of impersonation attacks, non-repudiation properties, authentication. The challenge here was the SIM low computing and storage versus the need to deal with large packages that may get out of devices. And the solution that we found, in fact, Sergio already introduced it, was to use SIM digital signatures of the payload's hash. Looking at the concrete flow here, there is an IoT device that has a device application with several sensors. These sensors send the sensor data to the device application. It sends that payload to the encryption application. And in this case, we applied GSMA IoT Safe here to define exactly the API to interact with the SIM. And the solution that we provided is exactly the signing of the payload's hash. After the signing of the SIM, the encryption application forwards the payload and sign dash to the cloud server, and the cloud server can verify the sign dash and make sure that the data came really from the device that it was expected to. To bootstrap the system and to understand why the system is secure, in the bootstrap phase, we generate a key pair. The private key is kept in the SIM. There is no API or access to access this private key. The public key is returned to be put in the key management system so that the payload or the sign dash can be verified after. There is also the private key that I already explained, and exactly the public key that I also explained already. Moving to the last solution, the network authorization based on IoT devices or IoT entities trustworthiness. The problem was to achieve a trustworthy communication authorization mechanism that would apply to most IoT devices. The challenge was exactly to use existing network functions to enforce the communication authorization without human intervention, being an autonomous system. The solution that we got, in fact, I already introduced it, was the automated manipulation of devices bitrate according to their trustworthiness or reputation. So, in this diagram, in fact, you can see part of what we saw in the last solution. The hardnet encryption part is still here. But here I add as well other ARCADIAN IoT components like behavior monitoring, self-protection, cyber threat intelligence. And then we have the reputation system. The reputation system receives the information about the trust of that can influence the trust of the device, and it builds a trust score with that information. After that, it provides that trust score and policies to a component that was built for the core network, that is communications authorization enforcement, which places the rules in the policy control functions of the network, trust-based rules, right? We translate the rules to rules that are understandable by the PCF. And after that, the communication is controlled according to that. So outgoing or incoming communication is controlled according to that. Moreover, this component has another function, which is of distributing the trust data, the trust information to the device secure element, to the SIM particularly. And in this case, the SIM will be able, for instance, to refuse to sign digital payloads if the device is found to be compromised. And if the SIM refuses to sign the payloads, anyone that receives those payloads will be able to not trust that information because it can be poisoned, it may be altered, something may have happened with that information. To finish, so just summing up, the SIM technologies are already critical in nowadays cybersecurity. They are trusted by telecom operators, governments, banks, and by everyone. Programmable networks continues to be a driver of innovation. In this case, automating actions in what we call a security sweet spot. And we believe that the SIM and programmable networks will have a potential to have an important role in ensuring security and trust in future networks and digital ecosystems. So we have GSMA IoT Safe. There are other standards coming up, like GSMA SAM for the ones that are aware of GSMA working groups. There is the SIM that is already present in billions of devices, so new security functions for the SIM will have quite a big impact in the society. And there is the possibility of having network policies and integrated automation with programmable networks.